test. All right, so I want to kind of work this problem together with you guys. This is from 1979, so it's really, really old. But like I said, these problems are incredibly repetitive. They come out all the time. The things that you need to start looking at, though, and not that you aren't, but I want to point out that it's probably a good idea from the start of these kinds of questions to begin looking at, what kind of material do we have? Point out whether we have conductors or insulators. We know that we have to treat them differently. So the thing that should be in your notes that it's kind of a big banner topic that, it's more important than the rules is that if you figure out that you have a conducting shell, then that immediately means the electric field inside is zero. We know that at the start. I don't need a rule for that. It's true for all metals, all conductors. So the moment you see the word conductor, if they're going to ask anything about the field that's going on, we know that the fields inside the conductors are zero. Morning, babe. So that has to be true. That does not mean the voltage is zero. Remember, the electric field and the voltage are related. The voltage is the distance change of the electric field. It's the grade of the electric field. So if the electric field is a zero, that just means the voltage is a constant in that place. There's no change in the electric potential. So don't assume the voltage is zero. Doesn't mean it can't be zero, just can't assume it. So get rid of those because I don't need them right now. That's just messing up my picture. So let's keep going a little bit further. It tells me that both shells have a total charge of positive Q. Now, this is where it's a little different than some. A lot of them have, one of them's positive, one of them's negative, something like that. We have two that are positive. So positive Q on the inside and positive Q on the outside. Express the answers to A, B, and E in terms of Q, A, B, C, and the Coulomb's law constant. And part A, using Gauss's law, derive an expression for the electric field from where R is between A and B. So pretty standard Gauss's law question. I think we're going to be a little bit more forward-looking and try and take a look at what they're going to ask in the future of this question. But since we're only being asked about what's going on inside the space between the inner shell and the outer shell, we start by drawing a Gaussian surface. Now, it shouldn't be a huge thing to say that this is got spherical symmetry. So we're going to use a sphere to describe this one, which means a Gaussian surface that is a sphere. And we choose that because it makes dealing with our Gauss's law portion of the problem relatively easy. Now, we've done these problems a lot, so I don't feel like it's too big a stretch for us to kind of jump through these pieces. The first thing that we had to do is talk about the flux, recognize that the flux is going to be the integral of E dot dA. We got to ask ourselves the three questions that go along with this. First, is the electric field constant everywhere along my shell? If it is, we can check off that box. Next, do we have a clear and bounded area? If it is, we can check off that box. And lastly, do we know the alignment of the electric field and the area? And for this one, it's all the same. We can check off that box. We have checked off our three boxes. And once we've kind of checked off those three boxes, we can perform the integral. This one, there's no work. It's just integral produces E times 4 pi r squared, but we have to specify that this r is between A and B, just so we are clear about it. And that's going to be our flux. And again, this doesn't produce a particularly complicated answer, but this does give us the portion of the Gauss's law dealing with the flux, E times 4 pi r squared. We have our epsilon naught out here, and now we have to deal with our Q enclosed, which is just capital Q. So when it says derive an expression for the electric field, we could have just written it down. And that wouldn't have been a huge deal to just write it down, but it says derive, which means we have to start with a principle, and they told us the principle to use, so we have to ensure that we are demonstrating Gauss's law. We can't cut any corners or anything like that. Now, it shouldn't take too much for me to add this real quick, but we should also probably just in our minds note that E is 0 whenever R is less than A, and E is also 0 for R between B and C. It's a good idea just to make sure we hammer that home so we don't lose track of that. All right, any question about this part? Pretty straightforward, right? So we go on to picture, you know, there's a big jump between A and B. It easily looks twice as big when squared would make that 4 times larger in the denominator. So even though the top of the fraction doubles, the bottom of the fraction goes up by a factor of 4. And then we add a little bit to it to get to the outside of C. So next page. Now, this one's not so bad. It doesn't really ask you to do very much. In fact, you don't have to do hardly anything. We've already done part of it. Write an expression for the electric field for R greater than C, between B and C, and less than A. Well, we've already done part of that. We know that the electric field is 0 for 2 of these, for R between B and C, and for R being less than A. We already covered that. It's inside inside our conducting shell. But be aware that just because it says, this particular one says I don't have to do any work for it, doesn't mean you might not be asked to qualify why this is true. But this one's great. It's not necessary to show your work, so we're kind of done. The only other part, it says R greater than C, but I don't have to show my work. And if I don't have to show my work, I know it's just going to be whatever I would have, for a point charge with the same amount of charge. Doesn't matter that it's conductor. The total charge is still 2Q. And this is for R greater than C. Any question about these? All right, so I think those two are pretty straightforward. It's the next part that might start getting a little more complicated. So before I go on, any questions to hear? All right. Because if you look at if it's drawn to scale, so I'm going to stop for a minute and I'm going to ask you guys to do this. It says on the axis below, sketch a graph of the electric field. And it's got A, B, C, and 2C clearly indicated. I think 2C is there just to give us a clear location someplace out away from the center, far enough away. I believe you need to have labels here. So I'll take a minute, let you guys work on this for a second, and then I'm going to kind of hit you guys up for what this should look like. Okay? All right, ready to go on this one? So I don't feel too terrible calling some folks out, since this was a relatively straightforward question, but I will allow somebody to tell me where to start my graph at 0. So where does my graph start on the y-axis at r equals 0? Luke says 0. So way to throw it in the chat so nobody can hear it, but I'll go with that. So Luke, what should the graph look like starting at 0? All right, so somebody else tell me what happens immediately at A. Now, Tang puts out QK over A squared. So I need to set kind of an arbitrary place on my axis to act as that. So I'm going to set right here and label QK over, and you said A squared, so I'll put A squared. And that's going to be a discontinuity in the graph. So the instant I leave the surface, I get this discontinuity. And Tang, what's the graph going to look like from here? Okay, that's fine. I'm not going to say exponential because it's not actually exponential. It is an inverse square. But I mean, I'm not sure I can tell the difference. You know, because how's an exponential how's an exponential decay a inverse decay and an inverse square decay? How do they compare? Exponential decay should be steepest of them. Maybe it depends on what's in the exponential. Inverse square should be more steep than an inverse, but we don't have enough information, and they're not going to care, just as long as you demonstrate that there's some kind of clear attenuation of the graph. But then once I hit B, what do I need to do here? Somebody else. All right, so I'm back at 0, and from there it stays at 0 until I get to C. And now, where should I place this portion of the graph? I think we all know that it's going to be another discontinuity. Q is twice as big, but we really don't have reference for how big C is compared to A. So you really can't go wrong. I just tend to make it a little higher, not because I think I know more. It's just that I can show the person who's grading that I kind of have a feel for the fact that there's going to be another discontinuity. It's going to reset what the y-axis is, and it's going to be some kind of decay. We don't have any relationship between A, B, and C to know their actual sizes unless we use the picture. Now, if we use the picture as our reference and assume the picture is drawn to scale, then this graph probably wouldn't look like this. If we assume that we're using the picture as our reference, then probably our picture would look more like this. Now, I'm saying that, well, probably need something more like that. But are they going to have us label out here? Sure, probably. I would if you can. Just be clear what you think these things are supposed to be, and you should be fine. The graph on the solution set looks something like this. It doesn't attenuate quite as much on the solution set, but it does show attenuation, like so. All right. Now, you don't have to put anything else, and you don't have to have any reference. Any questions about this graph? All right. Up till this point, I think this is a pretty straightforward problem, and then we reach this one. On the axis below, sketch a graph of the potential versus distance r from the center of the solid sphere. And question E actually asks for what the potential is at some point. Now, they just want you to sketch a graph. Can you sketch the graph without doing any calculation? Can you just get an idea for what the graph's potential should look like? If not, we can calculate the potential. But I'm hoping that something I said at the beginning of this discussion will help you here. So again, I want to take a quick pause, see if you guys can't perhaps work this out. And in a kind of a different way, what I'd like you to do is just hold your graph up to the screen if you're willing to share. We can take a look at everybody's and get an idea of who we think might have the right graph. So we're going to pause for, 60 seconds or so. But between the two of them, Tang would get more points than Ricardo. And here's the first part of the reason why. The electric potential inside the conductors is a constant, not necessarily zero. We don't know what that constant necessarily is, but we know that's going to be a flat line anywhere. So if I look at the beginning, I'm going to say that. Now remember, the other thing to think about is the electric potential increases as you go against the electric field. So as we approach the first edge of the shell from the outside, so if I have, as I approach this, I'm going against the electric field. So I know the electric field is getting greater and greater and greater. So my electric potential represents kind of the level of the land. Remember, it's like the gradient. So I'm going uphill until I reach a conductor. While in a conductor, there's no change in elevation. And then the moment I leave the conductor and I start going back into the area where there's an electric field, I've got to change in elevation until I get to a conductor. So if I start from far away, I'm going to have this general increase in the grade as I work against the potential. I'm going uphill. I have to do work to get my charged particle closer and closer and closer until I reach the conductor, and then it's flat. And then I'll have a similar work until I get to the next conductor, and then it's flat again. These need to be curved, though, to represent inverse functions. Not inverse squared, but inverse. Even if I don't want, remember, it just says determine here. So even if I don't want to do a lot of work to figure out the electric potential from a point charge is Q over 4 pi epsilon naught R. That's the electric potential from a point charge. And they already told us that this has to be the version of the point charge that we use, because they said that the electric potential was was 0 at infinity. So that means that this has to be the expression for the electric potential from a point charge. So on the outside edge, so I'm just going to draw the outside edge for C, the electric potential when I get to this point right here has to be 2Q over 4 pi epsilon naught times C. And it has to be this everywhere in this shaded region. It has to be a constant. And since that's what it is on the edge of C, that's also what it's going to be at the edge of B. So when it says determine the potential at R equals B, that's the answer. I'm not going to replace the C with B because I know that the potential had to increase right up until the edge of that first sphere, and there's no increase as I go from the edge of C to the edge of B, because everywhere in here there's no electric field, so the potential can't change as I go from here, from here to here. Now, immediately when I get here, it's going to start to change. It's going to start to increase again. Right up until I get to A. Now, tomorrow we're going to spend a little time with some focus on the electric potential and methods for calculating the electric potential, of which there are 3 methods to calculate the electric potential. And we're going to look at something we've not looked at before called the superposition of potential. It's something I kind of left out first semester because the word superposition is tough, but we're going to take a look at the idea of what's called superposition of potential. And it's an interesting way of dealing with something that wasn't asked in this problem, but would be the way you'd calculate the potential between 2 conductors. This problem's not so terrible because Q is positive for both. But what happens when we have, say, a negative Q tucked inside a positive Q? Things get a little bit more complicated. So we're going to end here for today. Reminder for that, to answer that question with a little more detail, remember that the electric potential can be calculated as dE dR in this case. I'm using R and not X, but because there's no change in E over R, this has to be a constant when the electric field is 0. that okay? All right. All right, folks. That's it for today. So I look forward to seeing you all tomorrow. There's going to be a video posted tomorrow I'd like you to take a look at. It's going to talk a little bit about potentials and some other shape stuff. We're going to talk about some other shapes this week. I've given reference to some particular FRQs I'd like you to look at. And I know you guys can look those up. So you might want to just